All right, chapter 7.2 deals with graphing exponential functions. So the graphs that we've learned in the past, we have a graph of a line. So when we just have an x all by itself, it's going to be some type of line. So we could have a line looking like this that's increasing. If the slope was negative, we could have a line like this. So just when we have x all by itself, it's going to be a line. When we have an x squared, so it could either look like this first equation that's in standard form, or it could look like the second one that's in vertex form. So we have an x squared, it's going to be a quadratic graph, which is the graph of a parabola. So anytime we see an x squared, our graph is going to be some type of U shape. The next graph we're going to learn is the graph of exponential functions. So now we have some number raised to an x. Our graph is going to look like this. So you guys have heard the term like increases exponentially, especially with this coronavirus. The curve increases exponentially. So it's going to be some type of graph that's going to start out along the x and then just shoot up and gets really high really fast. So the general form of an exponential function is going to be y is equal to some number. So we could have two numbers multiplied by each other. We could have just one number raised to the x. So the exponent x is the independent variable with the domain set of real numbers. So x can be anything. So x is what's changing that we pick. We pick a value for x, and it gives us some value for y. So we have two types of graphs. We have exponential decay, which means it's decreasing exponentially, and we have an exponential growth, which means that it's increasing exponentially. So here is our growth. So it goes up really quickly. Exponential decay, it goes down really quickly. Our asymptote is our x-axis. So our graphs are never going to touch the x-axis, but they're going to be really close. So no matter how small of a number we pick for this exponential growth graph, it's going to get really, really close to this x-axis line, but it'll never touch. So it's going to get super close, closer and closer and closer, but it'll never touch that line. Okay, now we get to the fun part, graphing. So what is the graph of y is equal to 2 raised to the x? So just like how we've graphed in the past, we're going to pick numbers for x, and we solve the equation, and we get numbers for y, and we just put those on our graph. So the numbers that we're always going to pick for x are going to be -1, 0, 1, and 2. So if we have 2 raised to the -1, any exponent that's negative changes this into a fraction. So if 2 raised to the -1 is on top, to make this a positive one, we put it on the bottom. So now we have 1 over 2 raised to the 1, which 2 raised to the 1 is just 1/2. So when we plug in x, our point's going to be -1. So we plug in -1 for x, we get 1/2 for y. So we're going to go to our graph. We're going to go to the left 1 and up 1/2. Next, we're going to plug in 0. So we have 2 raised to the 0. Anything raised to the 0 is going to be 1. So when we plug in 0 for x, our y is 1. So we stay at 0 and go up 1. Next, we're going to plug in 1. So we have 2 raised to the 1. So this is just 2. So our next point is going to be 1, 2. So we're going to go the right 1 and up 2. And our next point is going to be 2 that we plug in. So we have 2 raised to the 2. This is like saying 2 times 2, and 2 times 2 is 4. So when we plug in 2, we get 4. So we're going to go the right 2 and up 4. So our graph is going to look like this. So we have an exponential growth graph. Our next graph, we have 7 times 0.6 raised to the t. So in here we have 7 times 0.6 raised to the t, raised to the x. I'm going to change this to x. It doesn't matter. T is our variable, so it could be anything. So we could call it t, we could call it x. Same thing. So again, we're going to plug in the same values for x. We're going to stick with -1, 0, 1, and 2. So when we plug in 7 times 0.6 raised to the -1, this -1 makes 0.6 go on to the bottom. So the 7 stays on top because that -1 isn't the power of 7. 7 is just being multiplied to the whole thing. So 7 stays on top and the 0.6 goes on the bottom. So we have 7 divided by 0.6, which for this section you will need your calculator for the whole section. So on the quiz that's coming up, you will get to use your calculator. So we're just going to do 7 divided by 0.6, and we get 11.66. So when we plug in -1, our y is 11.66. Next, let's go and graph that. So we go to the left 1 and we go up 11.6. So it's just off our graph there. Next, we're going to plug in 0. So we have 7 times 0.6 raised to the 0. Anything raised to the 0 is 1, but it's only that 0.6 that's being raised to the 0. So we have 7 times 1. So 7 times 1 is 7. So when we plug in 0, our y is 7. So we're going to stay at 0 and go up 7. Next, we're going to plug in 1. So we have 7 times 0.6 raised to the 1. So this is just like saying 7 times 0.6. We're going to put that into our calculator. So 7 times 0.6 gives us 4.2. So when we plug in 1, we get 4.2. So we're going to go to our graph, go to the right one, and up 4.2. Last number is 2, so we have 7 times 0.6 squared. So we have 7 times. Now we need to figure out what 0.6 squared is. So in our calculator, we're going to do 0.6 squared, or you could do 0.6 times 0.6, and we get 0.36. And now we just multiply 7 times 0.36, which gives us 2.52. So when we plug in 2, we get 2.5. So we're going to go to our graph, we're going to go to the right 2 and up 2.5. So our graph here is going to look like this. So here we have an exponential decay graph. When the number that's being raised to the x, so the number that's right in front of the x, when it's less than 1, you're going to have a decaying graph. So when it's less than 1, so 0.6 is less than 1, your graph is going to decay. When it's greater than 1, it's going to be an exponential growth. So in the last example we did, the number right in front of the x was 2, and we saw that our graph was exponentially growing. So 2 is greater than 1. So when it's greater than 1, we have an exponential growth. When it's less than 1, we have an exponential decay. So here we have an exponential decay. So next we're going to look at a formula for exponential growth and decay. For growth or decay to be exponential, a quantity changes by a fixed percentage each time period. So we can use this formula when we're talking about money increasing by a certain percentage over a time period, which is what most of our examples are going to be. We could talk about like animals in the wild exponentially increasing or decreasing over a certain time period. So there's different things that you can use this formula for, but it's always going to be, you're always going to need a rate of growth, which is going to be your R. So our R is our rate of growth. Our rate of growth is always going to be some type of percent. So it'll tell us like 7% is our rate of growth or rate of decay. And this 7%, we need to change into a decimal. So whatever percent it gives us, we change it to a decimal by just moving the point 2 spaces. So the 7% is going to equate to the decimal of 0.07. Same thing if we had 5%, we would just move our decimal 2 places. So this would be like saying 0.05. So your rate of growth is always going to be a decimal. We are going to raise it to the t, which is going to be our number of time periods. So if it said like 6 years, our t would be 6. So t is the amount of time, and the initial amount is the amount that we start with. So if we're dealing with money and it says we start with $100 in our bank account, then our initial amount would be 100. And then amount after t time periods is what we're looking for. So that's just our final amount. So let's do an example. So you invested $1,000 in a saving account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? So let's rewrite our formula. We have our amount that we're looking for. So our amount after a certain amount of years is going to be our initial amount times 1 plus our rate raised to our t, which is the amount of time. So our variables that we need are going to be our initial amount, which is the lowercase a, our rate, and our time. So our initial amount, so we invested $1,000 into a saving account, so that's going to be our A. Next, our rate is always going to be the percentage. So this says 5%, but we need to change it to a decimal, so it's going to be 0.05. And then last, we have our time, which it says after 6 years, so our t is going to be 6. So now we just take everything and plug it into our formula. So we have the amount that we're looking for is equal to our starting amount, which is 1,000, times 1 plus our rate, which is 0.05, raised to the time, which is 6. So now we can put this into our calculator. So we have A of t is equal to 1,000, and we have 1.05 raised to the 6, which is 1.34. So we have 1.34 times 1,000, which is equal to 1,340. So if we invest 5% annually after 6 years, we'll end up with $1,340 into our account. When putting this part into the calculator, so this part, on the phone calculator, there's a button that has x raised to the y. So the way you would do it would be you type in 1.05 and then you push that button, x raised to the y, and then you would put 6 and then you just click the equal button and then it would give you 1.340 ... So you would type in your base first, then you click this button, and then you would click the exponent, so whatever it's raised to, and then the equal sign. So this is just how you would put it into the calculator. So next we have continuously compounded interest. So here we have our formula, which is A of t, so the amount in account at time t is equal to the principal. So this is what we start with. So our starting amount times e, which is just a fixed variable. So if you look in the calculator, there's an e button. It's kind of just like pi. It's just some number. And e is raised to the interest rate, which again will be a decimal. So it'll be a decimal as our rate, and the time t in years. So if we're continuously compounding something, the difference between this formula and the last one we had is that when it's continuously compounded, if we start with, let's say, $1,000 in our account, and we're earning $1 on it every day, so day 2, we would have $1,001, and then we would be earning interest on this new amount the next day. So it increases quicker than our last formula. So our example here is, suppose you won a contest at the start of 5th grade that deposited $3,000 in an account that pays 5% annual interest compounded continuously. How much you will have in the account when you enter high school 4 years later. Express the answer to the nearest dollar. So the formula we're going to use is our amount is equal to our principal times e raised to the r times t. So we need our principal, which is our starting amount, so our $3,000. Our e is just always going to be that e, and our rate is 5%, so we need to change this to a decimal, so we have 0.05, and our t is our time, so we're looking at 4 years later, so our t is 4. So our amount in our account is going to be 3,000. We're just plugging in all of our numbers now, so we have 3,000 times e raised to the 0.05 times 4. So we're going to put this into our calculator first. So we have 3,000 times e raised to 0.05 times 4, which is 0.2. And now we're going to say e raised to the 0.2. And again, on your phone calculator, there's an e button, so it's e to the x. So we are going to put 0.2, and then, so we click our 0.2, and then we click the e to the x button, and it'll compute automatically as 1.22. So we put whatever our thing is being, whatever e is being raised, and then we click this e to the x button. So we have 3,000 times 1.22. So now we put these two into our calculator, which gives us our amount as 3,664.21. Puts us to the nearest dollar, so we don't need this. So $3,664 is what we end up with in our account. So when we're continuously compounding our interest, if we start with $3,000 after 4 years, we're gaining $664 by doing nothing but leaving our money in the bank. So the money is just increasing just by being in the bank on its own. Okay, so this is 7.2. You guys have a homework assignment, which I'll go over a few of the questions. So for the first 5, you're graphing the function. So just like we did in the first few examples, we're just plugging in numbers for x. So we're going to plug in -1, 0, 1, and 2. And we're going to get numbers for y, and we just plug in those points and graph it. So that's going to be the first 5 questions. For number 7, we're identifying each function as linear, quadratic, or exponential. So we know linear is going to be an equation that just has an x. Quadratic is going to be our parabolas, which are x squared, and exponential is going to be that number raised to the x, so our x is going to be our exponent. Number 8 and number 9, you're going to use the first formula that we went over. So a of t is equal to our amount that we start with times 1 plus our rate raised to the t. So you're going to use this formula for 8 and 9. And then for 10 and 11, you're going to use our a of t is equal to p times e r t. So the principal, which here it gives you the principal, e is just that variable that we have in our calculator, r is our interest rate, but remember it has to be the decimal, and t is our time in years. So we're using this formula for 10 and 11. All right, email me if you guys have any questions. Have a good one. See you Friday.